Every night for thousands of years, humans have gazed up at the moon, seeing the same familiar face staring back at us. The same craters, the same dark seas, the same bright highlands that have inspired countless stories, myths and dreams. But what if I told you that we've only ever seen half the story? What if behind that familiar face lies a completely alien world, so different from what we know that it might as well be from another planet entirely? Tonight, we're embarking on a journey to one of the most mysterious places in our solar system. A realm that remained hidden from human eyes for all of recorded history until just 65 years ago. A place where the laws of physics seem to whisper secrets about the early universe, where ancient impacts have carved scars so massive they dwarf entire continents, and where discoveries are rewriting everything we thought we knew about our closest celestial neighbour. Welcome back to another exploration into the cosmos. I'm thrilled you've joined me tonight, and before we venture into this lunar mystery together, I'd love to know where in the world you're watching from and what draws you to these cosmic puzzles. If you find yourself captivated by these journeys, a quick like and perhaps subscribe to join our community would mean the world to me. It helps more curious minds discover these cosmic stories we're unraveling together. Get ready, the journey begins now. The story begins with a simple yet profound astronomical reality that has shaped human understanding of the moon for millennia. Our lunar companion is locked in what astronomers call synchronous rotation, a gravitational dance so precise that the moon takes exactly the same amount of time to rotate once on its axis as it does to orbit Earth. This cosmic choreography, perfected over billions of years of tidal forces, means that one hemisphere of the moon perpetually faces our planet, while the other remains forever turned away. For countless generations, this hidden hemisphere existed only in the realm of imagination. Ancient civilizations wove stories about the moon's mysterious nature, but none could have conceived that an entire world lay concealed behind the familiar face they observed each night. The Greeks called it Selene, the Romans lunar, but regardless of the name, they all saw the same side, the same patterns of light and shadow that have become humanity's shared lunar heritage. It wasn't until October 7th, 1959, that humanity first glimpsed the moon's hidden face. The Soviet Luna 3 spacecraft, carrying primitive cameras and transmission equipment, swung around our celestial neighbour and captured grainy, revolutionary photographs of terrain that no human had ever seen. Though the images were fuzzy and distorted by the limitations of 1950s technology, they revealed something extraordinary and unsettling. The far side of the moon looked nothing like the near side we knew so well. Where the familiar near side displayed vast, dark plains that ancient astronomers had mistaken for seas, the far side showed a landscape dominated by bright, heavily cratered highlands. The smooth basaltic maria that create the man-in-the-moon pattern were almost entirely absent. Instead, the hidden hemisphere presented a world that appeared more ancient, more battered, more alien than anyone had dared imagine. This first glimpse raised questions that would consume lunar scientists for generations. Why did the two hemispheres look so dramatically different? What cosmic forces had shaped this hidden world? And what secrets might this mysterious terrain hold about the moon's formation and the early history of our solar system? The answers to these questions would have to wait decades for more sophisticated missions and technologies. But even those early, imperfect images from Luna 3 revealed one undeniable truth. The moon was far more complex and mysterious than anyone had realized. The hidden hemisphere wasn't simply a mirror image of the familiar side. It was an entirely different world, shaped by different processes and holding different stories about the cosmic violence that had sculpted our solar system's early years. As space exploration advanced through the 1960s and beyond, each new mission to the moon brought fresh revelations about the stark differences between its two faces. The Apollo missions, focused on the near side for safety and communication reasons, provided humanity with its first close-up understanding of lunar geology. But the far side remained largely mysterious, visited only by robotic explorers and observed from orbit by increasingly sophisticated instruments. What emerged from these observations was a portrait of asymmetry so extreme that it challenged fundamental assumptions about planetary formation. The near side, with its abundant volcanic plains, told a story of a moon that had been geologically active well into its history, with massive lava flows filling ancient impact basins and creating the dark features visible to the naked eye from Earth. But the far side painted a different picture entirely, one of a world where volcanic activity had been limited and ancient impact craters remained largely unfilled and unmodified. The far side's crust proved to be significantly thicker than the near side's, sometimes by as much as 50 kilometers. This thickness had profound implications for the moon's geological evolution, affecting everything from the ease with which magma could reach the surface to the preservation of ancient impact structures. Where the near side's thinner crust had allowed molten rock to pour forth and create vast lava plains, the far side's thick crustal armor had largely prevented such volcanic resurfacing. But perhaps the most intriguing feature of the lunar far side is a structure so massive and ancient that it ranks among the most significant geological formations in the entire solar system. The South Pole Aitken Basin, stretching across roughly 2,500 kilometers of the moon's southern hemisphere, represents one of the largest and oldest impact craters ever discovered. This colossal scar on the lunar surface, carved by an asteroid collision approximately 4.3 billion years ago, offers a unique window into the moon's deep interior and the violent processes that shaped the early solar system. The formation of this basin was an event of almost unimaginable violence. An asteroid, possibly hundreds of kilometers in diameter, struck the moon with such force that it excavated material from depths that may have reached the lunar mantle itself. The impact was so powerful that some scientists theorize it may have caused the moon to shift on its axis, potentially contributing to the hemispheric differences we observe today. Within this ancient scar lies one of modern lunar science's most perplexing mysteries. Deep beneath the basin's floor, gravity measurements from NASA's Grail mission have revealed a massive anomaly, a concentration of dense material weighing more than 5 times the mass of Hawaii's Big Island. This mysterious mass, buried more than 300 kilometers below the surface, has sparked intense scientific debate about its nature and origin. The leading hypothesis suggests that this anomaly may be the remnant of the asteroid that created the basin, its iron-nickel core somehow embedded in the moon's upper mantle during the cataclysmic impact. If true, this buried metallic mass would represent a preserved piece of the early solar system, a relic from the era when planets and moons were still being battered by massive asteroid impacts. But the South Pole Aitken Basin holds secrets beyond its mysterious, buried mass. The impact that created it was so deep and violent that it may have exposed materials from the moon's interior that are found nowhere else on the lunar surface. These exotic materials, brought up from depths normally hidden beneath kilometers of crustal rock, offer scientists a unique opportunity to study the moon's internal composition without the need for deep drilling. Recent analysis of samples returned by China's Chang'e 6 mission from within this basin has revealed volcanic rocks dating back 2.8 billion years, significantly younger than most samples from the moon's near side. This discovery suggests that the far side remained volcanically active much longer than previously thought, challenging existing models of lunar thermal evolution and raising new questions about the processes that drove this extended geological activity. The presence of these relatively young volcanic rocks is particularly puzzling when considered alongside the far side's generally thick crust and limited volcanic plains. How did magma manage to reach the surface in this region, when it was largely prevented from doing so elsewhere on the far side? The answer may lie in the unique conditions created by the South Pole Aitken impact itself, which may have fractured the crust and created pathways for magma that persisted for billions of years. Among the most significant discoveries from the Chang'e 6 samples was the detection of creep basalts, rocks enriched in potassium, rare earth elements, and phosphorus. These materials were previously thought to be concentrated primarily on the Moon's near side, where they help explain the abundance of volcanic activity. The discovery of creep basalts on the far side challenges this understanding and suggests that the Moon's compositional asymmetry may have different origins than previously theorized. Creep materials are particularly important because they contain heat-producing radioactive elements that can drive volcanic activity long after a planetary body's initial formation heat has dissipated. Their presence on the far side raises intriguing questions about how the Moon's thermal evolution may have differed between its two hemispheres, and why volcanic activity persisted longer in some regions than others. The implications of these discoveries extend far beyond lunar science. The Moon serves as a preserved record of the early solar system, a world where ancient surfaces and impact structures remain largely unmodified by the weathering and geological processes that have erased similar features on Earth. By studying the Moon's far side, scientists are gaining insights into the cosmic bombardment that shaped all the inner planets during the solar system's violent youth. The extreme age and preservation of far-side impact structures provide a unique laboratory for understanding impact processes and their effects on planetary bodies. Unlike Earth, where erosion and plate tectonics have erased most evidence of early impacts, the Moon's far side preserves a detailed record of the projectiles that battered the inner solar system billions of years ago. These ancient impact structures also offer clues about the distribution and composition of asteroids in the early solar system. By studying the chemistry and mineralogy of impact melt rocks and crater structures, scientists can infer properties of the impacting bodies and gain insights into the processes that shaped planetary formation throughout our cosmic neighborhood. But the scientific importance of the Moon's far side extends beyond its role as a museum of early solar system history. The unique properties that make it so different from the near side also make it an ideal location for certain types of scientific observations and future exploration activities. The far side's position, permanently shielded from Earth's radio interference, creates one of the quietest electromagnetic environments in the inner solar system. This natural radio silence makes it an ideal location for radio astronomy, particularly for observations of the early universe at frequencies that are completely blocked by Earth's ionosphere. Radio telescopes operating from the lunar far side could potentially detect signals from the cosmic dark ages, the period in universal history when the first stars and galaxies were forming but had not yet begun shining visible light. These observations could revolutionize our understanding of cosmic evolution and provide insights into processes that occurred when the universe was only a few 100 million years old. NASA and other space agencies are already developing plans to take advantage of this unique environment. The proposed Lunar Crater Radio Telescope would use robotic systems to deploy a kilometer-diameter wire mesh antenna within a suitable crater on the far side, creating the largest filled aperture radio telescope in the solar system. Such an instrument could observe radio frequencies that are completely inaccessible from Earth-based telescopes. The Moon's far side also offers unique advantages for other types of astronomical observations. The lack of atmospheric interference, combined with the Moon's stable surface and low seismic activity, could provide ideal conditions for optical and infrared telescopes. The lunar environment's lack of weather, wind, and atmospheric disturbances would allow for observations of unprecedented clarity and stability. Beyond its scientific value, the far side's unique properties also make it an intriguing location for future lunar bases and resource extraction activities. The permanently shadowed regions near the lunar poles, many of which are located on or near the far side, contain some of the coldest environments in the solar system. These regions serve as natural cold traps, preserving volatile materials like water ice that would quickly sublimate in sunlit areas. Recent discoveries have confirmed the presence of significant water ice deposits in these permanently shadowed regions, with some craters estimated to contain millions of tons of accessible water ice. This resource could be crucial for future lunar exploration, providing not only drinking water for astronauts, but also the raw materials for rocket fuel production through the splitting of water into hydrogen and oxygen. The extraction and utilization of lunar water ice could transform space exploration by providing a refueling station for missions to Mars and the outer solar system. Rather than carrying all necessary propellant from Earth's deep gravity well, spacecraft could refuel at lunar facilities, dramatically reducing the cost and complexity of deep space missions. As we continue our exploration of the Moon's hidden hemisphere, each new discovery adds layers to an increasingly complex and fascinating picture. The far side of the Moon is not simply the dark side of popular imagination, but a world of ancient impacts, mysterious anomalies, and unique opportunities that continues to challenge our understanding of planetary formation and evolution. The story of the Moon's far side is still being written, with each new mission and technological advancement revealing fresh insights into this alien yet familiar world. From the massive buried anomalies beneath ancient impact basins to the surprisingly young volcanic rocks that speak of extended geological activity, the hidden hemisphere continues to surprise and intrigue scientists around the world. The differences between the Moon's two hemispheres run deeper than surface geology, extending into realms that challenge our most fundamental understanding of planetary science. When scientists began analysing data from increasingly sophisticated lunar missions, they discovered that the asymmetry between near and far sides represents one of the most extreme examples of hemispheric dichotomy found anywhere in the solar system. The chemical composition of rocks from the far side tells a story of processes so different from the near side that they might as well describe separate worlds. Where Apollo samples from the near side revealed abundant traces of titanium, iron, and other heavy elements, typical of basaltic volcanism, the far side materials showed a markedly different signature. The rocks were enriched in aluminum and calcium, characteristic of the ancient highland materials that form the Moon's primordial crust. This compositional dichotomy extends beyond simple surface differences. Deep within the Moon's interior, seismic studies have revealed structural asymmetries that mirror the surface variations. When Apollo astronauts deployed seismometers during their missions, these sensitive instruments detected moonquakes and meteor impacts that sent seismic waves propagating through the lunar interior. The patterns of these waves revealed a Moon that was far from uniform in its internal structure. The seismic data painted a picture of a lunar interior with distinct layers and unexpected properties. Some of the most intriguing findings came from the analysis of deep moonquakes, seismic events that originated hundreds of kilometers below the surface. These deep tremors exhibited characteristics unlike anything seen in terrestrial earthquakes, persisting for remarkably long periods and maintaining their amplitude in ways that suggested the Moon's interior possessed unusual properties. The prolonged ringing of seismic waves through the lunar interior led some researchers to describe the Moon as ringing like a bell when struck by large impacts. This unusual seismic behavior suggested that the Moon's interior might be partially hollow or contain large void spaces, though subsequent analysis has provided more nuanced explanations involving the Moon's unique thermal and compositional structure. The mystery deepened when scientists compared seismic wave propagation patterns from the near and far sides. Waves travelling through the far side's thicker crust showed different characteristics than those propagating through the near side, confirming that the hemispheric differences extended throughout the moon's structure. The far side's crustal thickness variations created distinct seismic signatures that helped researchers map the moon's internal architecture with unprecedented detail. These structural differences have profound implications for understanding how the moon formed and evolved. The leading theory suggests that the moon originated from a Mars-sized object called Theia that collided with the early Earth approximately 4.5 billion years ago. This giant impact ejected massive amounts of material into orbit around Earth, which eventually coalesced to form our lunar companion. But if the moon formed from such a catastrophic collision, why did it develop such extreme hemispheric asymmetry? The answer may lie in the complex physics of planetary accretion and the unique circumstances of the moon's early evolution. Computer simulations suggest that the moon may have initially formed much closer to Earth than it is today, experiencing intense tidal heating that kept much of its interior molten for extended periods. During this early phase, the moon's rotation was likely much faster than today, and its orbit was highly elliptical. The combination of tidal forces, rotational dynamics, and ongoing bombardment from asteroids and comets may have created conditions that preferentially concentrated certain materials on one hemisphere while depleting them on the other. The South Pole Aitken impact may have been the defining event that locked in these hemispheric differences. The massive collision not only created the largest impact basin in the solar system, but may have also triggered hemisphere-scale convection in the moon's interior. Computer models suggest that the impact's energy could have initiated convection patterns that transported heat-producing radioactive elements toward the near side, creating the conditions for sustained volcanic activity there, while leaving the far side relatively depleted. This redistribution of radioactive elements would explain many of the observed differences between the hemispheres. The concentration of uranium, thorium, and potassium on the near side would have provided the heat necessary to drive volcanic activity for billions of years, creating the extensive lava plains we see today. Meanwhile, the far side, depleted of these heat sources, would have cooled more rapidly and retained its ancient, heavily cratered appearance. Recent orbital missions have provided increasingly detailed maps of these elemental distributions, confirming that radioactive elements are indeed concentrated on the near side. The Lunar Prospector mission's gamma-ray spectrometer created comprehensive maps showing the distribution of uranium, thorium, and potassium across the lunar surface, revealing patterns that strongly support the hemispheric redistribution hypothesis. But the story becomes even more complex when we consider the role of late-stage volcanic activity on the far side. The discovery of 2.8 billion-year-old basalts in the South Pole Aitken Basin challenges simple models of hemispheric evolution. How could volcanic activity persist on the far side for so long if it was truly depleted of heat-producing elements? The answer may lie in the unique conditions created by the basin-forming impact itself. The massive collision not only excavated enormous amounts of material, but also created deep fractures in the lunar crust that could serve as conduits for magma transport. Even small amounts of radioactive heating in the moon's interior could drive volcanism if efficient pathways existed for magma to reach the surface. The discovery of creep materials in far-side samples adds another layer to this puzzle. These potassium, rare earth element, and phosphorus-rich rocks were thought to be primarily a near-side phenomenon, concentrated in regions like Oceanus Procellarum, where they contributed to sustained volcanic activity. Finding similar materials on the far side suggests that the moon's early differentiation was more complex than previously understood. Creep represents the final products of lunar magma ocean crystallization. the dregs of a global molten layer that existed during the Moon's earliest history. As this magma ocean slowly cooled and crystallized, dense minerals sank toward the interior, while lighter materials floated toward the surface. Creep represents the last liquid to crystallize, enriched in elements that didn't fit easily into the crystal structures of common lunar minerals. The presence of creep on both hemispheres suggests that this late-stage differentiation product was initially distributed more evenly than current surface concentrations would suggest. Subsequent processes, possibly including the South Pole Aitken impact and its aftermath, may have redistributed these materials and created the asymmetric patterns we observe today. Understanding these processes is crucial for interpreting the Moon's role as a recorder of early solar system history. The lunar surface preserves evidence of the late heavy bombardment, a period approximately 4 billion years ago when the inner solar system experienced an intense spike in asteroid and comet impacts. This bombardment may have been triggered by gravitational instabilities in the outer solar system that sent icy bodies streaming inward toward the Sun. The far side's heavily cratered terrain provides a particularly well-preserved record of this ancient bombardment. Unlike the near side, where volcanic activity has obscured many impact structures, the far side retains craters from throughout lunar history. These ancient scars serve as windows into the population of projectiles that battered the inner planets during their early evolution. By studying the size distribution, spatial patterns, and ages of far-side craters, scientists can reconstruct the flux of impacting bodies over time and understand how this bombardment shaped planetary surfaces throughout the solar system. The insights gained from lunar crater studies have applications far beyond our own solar system, informing our understanding of planet formation and evolution around other stars. The preservation of ancient surfaces on the far side also makes it an ideal location for studying the effects of space weathering, the gradual alteration of surface materials by solar wind particles, cosmic rays, and micrometeorite impacts. Over billions of years, these processes modify the optical and chemical properties of surface materials, creating the characteristic appearance of airless planetary bodies. Understanding space weathering is crucial for interpreting remote sensing observations of asteroids, comets, and other airless bodies throughout the solar system. The Moon serves as a natural laboratory where scientists can study these processes in detail and develop models that can be applied to other worlds. The far side's unique environment also offers unprecedented opportunities for astronomical observations that are impossible from Earth. The Moon's position between Earth and distant cosmic sources creates a natural radio shadow that blocks terrestrial interference across a wide range of frequencies. This radio-quiet environment is particularly valuable for low-frequency radio astronomy, where Earth's ionosphere creates an impenetrable barrier to ground-based observations. Radio waves at frequencies below about 30 MHz carry information about some of the most fundamental processes in the universe. These low-frequency signals can reveal details about the cosmic dark ages, the period between the universe's initial cooling and the formation of the first stars. During this era, neutral hydrogen-filled space and could only be observed through its characteristic 21 centimeter emission line, redshifted to much longer wavelengths by cosmic expansion. A radio telescope operating from the lunar far side could potentially detect these ancient signals and provide direct observations of cosmic structure formation during the universe's first few 100 million years. Such observations would complement and extend the capabilities of space-based missions like the James Webb Space Telescope, which can observe the first galaxies in infrared light but cannot peer back to the pre-stellar era. The technical challenges of deploying and operating a radio telescope on the lunar far side are substantial but not insurmountable. The proposed Lunar Crater Radio Telescope, would require sophisticated robotic systems capable of deploying wire mesh antenna elements across kilometre-scale distances within a suitable impact crater. The natural bowl shape of large craters provides an ideal geometry for creating a spherical reflector that could focus radio waves onto sensitive receivers. Such a facility would need to operate autonomously during the lunar night, when radio interference from the sun is minimized and the most sensitive observations can be conducted. The lunar night lasts approximately 14 Earth days, providing extended periods of stable observing conditions unavailable from any Earth-based facility. The scientific potential of far-side radio astronomy extends beyond cosmological observations. Low-frequency radio waves can penetrate deep into planetary interiors, making them valuable for studying the subsurface structure of planets and moons throughout the solar system. A lunar radio telescope could conduct detailed studies of Jupiter's magnetosphere, Saturn's ring system, and the subsurface oceans of icy moons like Europa and Enceladus. The far side also offers unique advantages for other types of astronomical observations. Optical telescopes operating in the lunar environment would be free from atmospheric disturbances that limit ground-based observations. The moon's stable surface and minimal seismic activity would provide an exceptionally steady platform for high-resolution imaging of distant astronomical objects. The lack of atmospheric scattering would allow lunar telescopes to observe across the entire electromagnetic spectrum, from radio waves through gamma rays, without the filtering effects that limit Earth-based observations. This broad spectral coverage could enable comprehensive studies of astronomical phenomena that require simultaneous observations at multiple wavelengths. The moon's lower gravity, about 1/6 that of Earth, would also allow for the construction of much larger telescope structures than are practical on Earth. The reduced structural loads would enable the deployment of vast antenna arrays or mirror assemblies that would be impossible to support against terrestrial gravity. These advantages have led to serious proposals for lunar astronomical facilities, ranging from individual telescopes to comprehensive observatories that could revolutionize our understanding of the universe. The challenges of constructing and maintaining such facilities in the harsh lunar environment are significant, but the potential scientific returns justify continued investigation of these concepts. The far side's role in future human space exploration extends beyond its scientific value. The permanently shadowed regions near the lunar poles, many located on or extending onto the far side, contain some of the most valuable real estate in the solar system. These areas combine several crucial advantages for sustained lunar operations: abundant water ice resources, extended periods of sunlight on nearby peaks for solar power generation, and relatively mild thermal conditions compared to the extreme temperature swings experienced elsewhere on the Moon. Water ice in permanently shadowed regions represents more than just a convenient resource for future lunar inhabitants. The ability to extract and process lunar water could transform space exploration by providing locally produced rocket fuel for missions to Mars and beyond. The chemical splitting of water into hydrogen and oxygen creates high-performance propellants that could enable refueling operations throughout the inner solar system. The economic implications of lunar water extraction are staggering. Current launch costs make it prohibitively expensive to transport large quantities of water or fuel from Earth's surface to deep space. A lunar refueling infrastructure could reduce the mass requirements for interplanetary missions by orders of magnitude, opening up possibilities for sustained exploration of Mars, the asteroid belt, and the outer solar system. But accessing these resources will require overcoming substantial technical challenges. Permanently shadowed regions experience some of the coldest temperatures in the solar system, approaching absolute zero in some locations. Operating robotic equipment in these extreme conditions, while extracting and processing water ice, will push the boundaries of current technology. The preservation of water ice in these regions over billions of years tells us something profound about the Moon's thermal history and the sources of volatiles in the inner solar system. Some of this ice may have originated from cometary impacts during the late heavy bombardment, preserving ancient water from the outer solar system in these natural cold traps. Isotopic analysis of lunar ice could provide insights into the sources of Earth's water and the delivery mechanisms that brought volatiles to the inner planets. Understanding these processes is crucial for assessing the potential habitability of rocky exoplanets and the likelihood of finding water-rich worlds around other stars. The far side continues to surprise researchers with discoveries that challenge our understanding of lunar evolution and planetary science more broadly. Each new mission reveals additional complexity in what was once thought to be a geologically simple world. From the massive buried anomalies beneath impact basins to the unexpected preservation of ancient magnetic signatures, the hidden hemisphere keeps rewriting the textbooks. Recent analysis of magnetic field measurements has revealed that the Moon once possessed a global magnetic field comparable in strength to Earth's current field. This ancient magnetosphere left its signature in lunar rocks, creating a record of magnetic field evolution that spans billions of years. The far side preserves some of the strongest and most ancient magnetic signatures, suggesting that it may hold crucial clues about the Moon's magnetic history. Understanding how and why the Moon's magnetic field evolved provides insights into the thermal and dynamic evolution of its interior. The generation of planetary magnetic fields requires convection in electrically conducting fluids, typically molten metal cores. The Moon's small size should have allowed its core to cool and solidify relatively quickly, yet evidence suggests that magnetic field generation persisted for much longer than simple cooling models would predict. The preservation of strong magnetic signatures on the far side may be related to the hemisphere's thicker crust and different thermal history. These magnetic anomalies could represent fossil records of impact-induced magnetic field generation, or evidence for more complex core dynamics than previously understood. As we continue peeling back the layers of lunar mystery, the far side emerges not just as a complement to the familiar near side, but as a world unto itself with its own unique story of formation, evolution, and preservation. Each crater, each mineral grain, each magnetic anomaly adds another piece to the vast puzzle of how worlds form and change over cosmic time. The hidden hemisphere has transformed from a curiosity glimpsed in grainy photographs to a crucial piece of the solar system story, one that continues to yield surprises and challenges our most fundamental assumptions about planetary science. And as we prepare for the next chapter of lunar exploration, with new missions, advanced instruments, and eventually human explorers returning to the Moon, the far side stands ready to reveal even more of its carefully guarded secrets. The technological marvels that have allowed us to study the far side represent some of humanity's most sophisticated achievements in space exploration. When NASA's Lunar Reconnaissance Orbiter began its systematic survey of the Moon in 2009, it carried instruments capable of peering through the lunar surface and mapping subsurface structures with unprecedented precision. The spacecraft's laser altimeter could measure surface elevations to within centimeters, while its cameras captured images detailed enough to reveal features smaller than a dining room table. But perhaps the most revolutionary tool for understanding the far side has been the Gravity Recovery and Interior Laboratory mission, known as GRAIL. This ambitious project employed two spacecraft flying in precise formation around the Moon, constantly measuring tiny variations in the gravitational field as they orbited. When one spacecraft passed over a region of higher density, it would experience a slight acceleration that could be detected by monitoring the radio signals passing between the two vehicles. The GRAIL mission's discoveries beneath the South Pole Aitken Basin rank among the most startling revelations in planetary science. Deep within the Moon's interior, buried beneath kilometers of crustal rock, lies a mass so dense and extensive that it defies easy explanation. This subsurface anomaly stretches across hundreds of kilometers and penetrates deep into the lunar mantle, representing a concentration of material unlike anything found elsewhere in the solar system. The leading explanation for this buried treasure suggests we're looking at the fossilized remains of the asteroid that created the basin itself. When that ancient impactor struck the moon with unimaginable violence, its metallic core may have become embedded in the lunar interior like a cosmic bullet frozen in time. If this interpretation is correct, we have preserved within our moon a pristine sample of the early solar system, a piece of the primordial disk from which all planets formed. The implications extend far beyond lunar science. This buried metallic mass could represent our most accessible sample of early solar system materials, preserving isotopic signatures and chemical compositions that have been erased elsewhere by billions of years of geological processing. Future missions might attempt to reach these materials through deep drilling operations, potentially revolutionizing our understanding of planetary formation throughout the galaxy. The mystery deepens when we consider the basin's role in shaping the moon's subsequent evolution. Computer simulations suggest that the South Pole Aitken impact may have triggered convection patterns in the lunar interior that persisted for hundreds of millions of years. These convection cells could have transported heat-producing elements from the impact site toward other regions of the moon, creating the chemical asymmetries we observe today. This process might explain one of the moon's most perplexing characteristics: the concentration of radioactive elements in a region called the Procelarum Creep terrain on the near side. This vast province, visible as the dark areas that form the man in the moon pattern, contains elevated levels of uranium, thorium, and other heat-producing elements that sustained volcanic activity long after the moon's initial formation heat had dissipated. The discovery that similar materials exist on the far side, albeit in different concentrations and distributions, suggests that the moon's early differentiation was far more complex than previously imagined. Rather than a simple layered structure formed by straightforward crystallization of a global magma ocean, we're seeing evidence for dynamic processes that redistributed materials across hemisphere-scale distances. Recent analysis of Chang'e 6 samples has revealed additional complexities in this story. The volcanic rocks returned from the far side show isotopic signatures that indicate they formed from a mantle source that had been severely depleted in certain elements. This ultra-depleted signature suggests that the far side mantle underwent extensive processing, possibly through multiple episodes of partial melting that stripped away easily extracted components. The timing of this depletion remains uncertain, but it may be linked to the massive impacts that shaped the moon's early history. Each giant collision would have generated enormous amounts of heat and potentially triggered widespread melting in the lunar interior. The cumulative effects of multiple large impacts could have created the complex chemical zonation we observe in lunar samples today. Understanding these processes is crucial for interpreting the moon's role as a witness to the early solar system's violent history. The lunar surface preserves a record of the late heavy bombardment, but the chemical signatures locked within lunar rocks tell an even more detailed story about the projectiles that struck during this crucial period. The far side's crater population provides unique insights into this ancient bombardment. While the near side's crater record has been partially obscured by volcanic activity, the far side preserves impact structures spanning the entire history of lunar bombardment. These craters range from the massive ancient basins formed during the solar system's earliest epochs to small fresh craters created by recent impacts. Statistical analysis of crater-size distributions reveals patterns that constrain models of early solar system dynamics. The size-frequency relationships of far-side craters match theoretical predictions for populations of asteroids and comets that would have been present during different periods of solar system evolution. This agreement provides strong support for our understanding of how planetary bombardment rates have changed over time. But the crater record also reveals surprises that challenge conventional wisdom about impact processes. Some far-side impact basins show evidence for multiple impact events occurring within relatively short time periods, suggesting that the early bombardment may have been more clustered in time than previously thought. These temporal clusters might reflect gravitational instabilities in the outer solar system that periodically sent swarms of projectiles streaming toward the inner planets. The preservation of these ancient impact structures on the far side also provides natural laboratories for studying impact physics under conditions that no longer exist elsewhere in the solar system. The Moon's lack of atmosphere and geological activity means that impact craters remain largely unmodified for billions of years, preserving details about shockwave propagation, melt generation, and crater modification that have been erased from more geologically active worlds. Advanced computer simulations now allow researchers to model these ancient impacts with remarkable detail, incorporating everything from the impactor's velocity and composition to the target's thermal state and structural properties. When these models are compared with observations of actual lunar craters, they reveal insights about impact processes that apply throughout the solar system and beyond. The far side's role as a cosmic museum extends beyond impact craters to preserve evidence of other fundamental processes that shaped the early solar system. The ancient highland rocks that dominate the far side landscape represent some of the oldest solid materials in our planetary system, crystallized from the global magma ocean that enveloped the newly formed Moon. These primordial rocks contain isotopic signatures that constrain models of lunar formation and early evolution. The ratios of different oxygen isotopes in lunar highland samples, for example, provide crucial tests of the giant impact hypothesis for lunar origin. The remarkably similar oxygen isotope compositions of Earth and Moon samples support the idea that both bodies formed from the same reservoir of material, as would be expected if the Moon originated from Earth-orbiting debris created by a giant impact. But subtle differences in other isotopic systems hint at more complex processes operating during the Moon's formation. Some elements show small but measurable differences between Earth and lunar compositions, suggesting that the impact event may have involved more than simple mixing of terrestrial and impactor materials. High-temperature processes during the impact may have caused isotopic fractionation that left distinctive signatures in the resulting Moon. The far side's ancient rocks also preserve evidence of the Moon's earliest magnetic field. Paleomagnetic studies of highland samples reveal that the Moon possessed a surprisingly strong magnetic field during its first billion years, comparable in intensity to Earth's current field. This ancient magnetosphere would have provided some protection against solar wind erosion and cosmic ray bombardment, potentially preserving volatile materials that might otherwise have been lost to space. The discovery of this ancient magnetic field raises fundamental questions about the Moon's early thermal state and interior dynamics. Generating a planetary magnetic field requires convection in electrically conducting fluids, typically molten metal in a planet's core. The Moon's small size should have led to rapid cooling and solidification of its core, yet the paleomagnetic evidence suggests that core convection persisted for much longer than simple thermal models would predict. One possible explanation involves the gravitational stirring caused by the Moon's changing orbital distance from Earth. Early in its history, the Moon orbited much closer to our planet and experienced stronger tidal forces that could have provided additional energy to drive core convection. As the Moon gradually moved away from Earth due to tidal friction, this additional energy source would have diminished, eventually allowing the core to solidify and magnetic field generation to cease. The timing of magnetic field decay, as recorded in lunar rocks of different ages, provides crucial constraints on models of early Earth-Moon evolution. By studying magnetic signatures preserved in samples from different lunar regions and time periods, researchers can reconstruct the history of core dynamics and orbital evolution with unprecedented detail. The far side's magnetic anomalies also offer insights into impact-related magnetic field generation. Some of the strongest magnetic signatures on the Moon are found in regions antipodal to major impact basins, suggesting that basin-forming impacts may have temporarily enhanced magnetic field strength through shock-related processes. These impact-generated magnetic fields could have persisted for thousands of years after the initial collision, leaving permanent magnetization in crustal rocks. Understanding these processes has implications for magnetic field generation on other planetary bodies, particularly smaller worlds, that might not be expected to sustain long-lived magnetic fields through conventional core dynamo processes. Mars, for example, shows evidence of ancient magnetic fields that may have been generated through similar impact-related mechanisms. The search for water on the lunar far side has revealed deposits that could transform our approach to space exploration. While the most abundant ice deposits are found in permanently shadowed craters near the poles, smaller concentrations have been detected throughout the far side highlands. These widely distributed water reservoirs suggest that volatile delivery to the Moon was a global process rather than being restricted to polar regions. The discovery of water in unexpected locations challenges our understanding of how volatiles behave in the lunar environment. Solar wind bombardment continuously deposits hydrogen atoms on the lunar surface, where they can combine with oxygen in silicate minerals to form hydroxyl groups and eventually water molecules. This process operates continuously across the entire lunar surface, potentially creating a renewable water resource that could be harvested by future missions. But the preservation of water in non-polar regions remains puzzling. Without the extreme cold of permanently shadowed craters, most surface water should quickly sublimate and be lost to space. The fact that water signatures persist in other locations suggests that complex microenvironmental conditions may allow for volatile retention in ways that current models don't fully capture. Recent laboratory experiments have revealed that water molecules can become trapped within the crystal structures of lunar minerals through various processes. Impact heating can drive water into mineral lattices, while solar wind implantation can create hydroxyl groups that are stable at lunar temperatures. These processes could create distributed water reservoirs throughout the lunar crust that are far more extensive than previously imagined. The implications for future lunar exploration are profound. Rather than being restricted to polar regions for water access, lunar bases could potentially be established anywhere on the Moon with access to locally extractable water resources. This flexibility would allow mission planners to choose base locations based on scientific value, strategic importance, or logistical convenience, rather than being constrained by resource availability. The far side's unique electromagnetic environment continues to attract attention from radio astronomers eager to exploit its natural shielding properties. Earth's radio interference extends well beyond our planet's surface, creating a sphere of electromagnetic noise that can overwhelm sensitive radio receivers throughout the inner solar system. Only the Moon's far side offers a location where this interference is completely blocked, creating a radio quiet zone unmatched anywhere else in our cosmic neighborhood. The scientific potential of this radio silence becomes apparent when we consider the frequency ranges that are completely inaccessible from Earth-based observations. Low-frequency radio waves carry information about some of the most fundamental processes in the universe, but they cannot penetrate Earth's ionosphere. A radio telescope operating from the lunar far side could observe these blocked frequencies and potentially detect signals from the cosmic dark ages the period between the universe's initial cooling and the formation of the first stars. These observations would provide direct information about cosmic structure formation during the universe's first few hundred million years, complementing and extending the capabilities of optical and infrared telescopes that can only observe the universe after star formation began. The combination of far-side radio observations with other astronomical data could revolutionize our understanding of cosmic evolution and the processes that led to the formation of galaxies, stars, and ultimately planets like our own. The technical challenges of deploying radio telescopes on the lunar far side are substantial, but not insurmountable. The proposed Lunar Crater Radio Telescope would require sophisticated robotic systems capable of precise construction operations in the challenging lunar environment. The deployment of kilometer-scale antenna arrays within impact craters would push the boundaries of current robotic technology, requiring autonomous systems capable of complex manipulation tasks without direct human supervision. Power generation and thermal management present additional challenges for far-side operations. The lunar night lasts approximately 14 Earth days, requiring energy storage systems capable of sustaining operations through extended periods without solar power. The extreme temperature swings between lunar day and night, ranging from over 120 degrees Celsius in sunlight to minus 230 degrees Celsius in shadow, create thermal stresses that must be carefully managed to ensure equipment survival. Communication with Earth presents perhaps the greatest operational challenge for far-side missions. Direct radio communication is impossible due to the Moon's blocking effect, requiring relay satellites positioned at gravitationally stable points between Earth and Moon. China's successful deployment of the Queqiao relay satellite for their Chang'e 4 and Chang'e 6 missions has demonstrated the feasibility of this approach, but it adds complexity and potential failure points to any far-side operation. Despite these challenges, the scientific returns from far-side radio astronomy could justify the substantial investments required. The ability to observe previously inaccessible radio frequencies would open entirely new windows on the universe, potentially revealing phenomena that remain completely unknown to current astronomy. The far side's radio quiet environment represents one of the most valuable scientific resources in the solar system, one that becomes increasingly precious as Earth's radio interference continues to grow with advancing technology. The geological diversity of the far side continues to surprise researchers as more sophisticated analysis techniques are applied to return samples and orbital data. Recent studies have identified distinct geological provinces on the far side, each with characteristic mineral compositions, crater densities, and thermal histories. These provinces appear to represent different episodes in lunar evolution, preserving evidence of processes that operated at different times and under different conditions. The South Pole Aitken Basin represents perhaps the most geologically complex province, containing materials excavated from unprecedented depths during the basin-forming impact. Within this massive structure, researchers have identified zones of different composition that may represent layers of the lunar interior exposed by the impact event. Some regions show evidence of materials that may have originated from the lunar mantle, providing rare opportunities to study the Moon's deep interior composition without the need for drilling. Other far-side provinces preserve evidence of different types of volcanic activity, ranging from ancient highland volcanism that occurred during the Moon's earliest history to younger basaltic eruptions that filled impact craters billions of years after their formation. The diversity of volcanic products suggests that the lunar interior was more compositionally heterogeneous than previously thought, with different regions producing magmas of varying composition at different times. Understanding this geological diversity is crucial for interpreting the Moon's role in early solar system history and for planning future exploration missions. Different geological provinces offer different scientific opportunities and resource potential, requiring careful evaluation to optimize the scientific return from limited mission resources. The far side also preserves evidence of processes that may have operated throughout the early solar system, but have been erased from more geologically active worlds. The ancient impact melt sheets found within far side basins, for example, preserve records of shock metamorphism under conditions that no longer exist in the inner solar system. These materials provide natural laboratories for understanding how rocky materials behave under extreme conditions of pressure and temperature. Studies of far-side impact melts have revealed complex relationships between shock pressure, temperature, and mineral transformation. Some minerals show evidence of having been compressed to pressures exceeding those found deep within planetary interiors, while others preserve textures indicating rapid cooling from temperatures well above their melting points. These extreme conditions created new mineral phases and crystal structures that provide insights into fundamental materials science as well as planetary impact processes. The preservation of these shock features on the far side contrasts sharply with their general absence from Earth, where erosion and geological activity have erased most evidence of ancient impacts. The Moon's far side thus serves as a unique repository of information about impact processes that shaped all terrestrial planets during the solar system's violent youth. As we stand at the threshold of a new era in lunar exploration, the far side beckons with promises of discoveries that could transform our understanding of planetary science, cosmology, and our place in the universe. The hidden hemisphere that remained mysterious for all of human history until just decades ago continues to reveal secrets that challenge our most fundamental assumptions about how worlds form and evolve. The technological capabilities that will enable the next phase of far-side exploration are rapidly advancing. Robotic systems capable of autonomous operation in the harsh lunar environment are becoming increasingly sophisticated, while communication technologies are evolving to support complex operations on the Moon's hidden hemisphere. Power systems designed for extended lunar night operations are approaching practical deployment, and life support technologies for eventual human exploration continue to mature. The scientific instruments planned for future far-side missions represent quantum leaps beyond current capabilities. Advanced spectrometers will be able to identify mineral compositions with unprecedented precision, while ground-penetrating radars will map subsurface structures to depths of kilometers. Seismometer networks will monitor moonquakes and provide detailed images of the lunar interior, while sample return missions will bring back carefully selected materials for analysis in terrestrial laboratories. But perhaps the most exciting aspect of future far-side exploration lies in its potential to answer questions we haven't yet learned to ask. Each new discovery about the hidden hemisphere has revealed unexpected complexity and opened new avenues of investigation. As our tools become more sophisticated and our presence on the far side becomes more sustained, we can expect to encounter phenomena that will require entirely new frameworks for understanding. The far side of the Moon stands as a testament to the power of exploration to expand human knowledge and challenge our preconceptions about the universe. From a mysterious hidden hemisphere glimpsed in grainy photographs, it has emerged as one of the most scientifically valuable locations in our solar system, offering unique insights into planetary formation, cosmic evolution, and the potential for life beyond Earth. As missions continue to peel back the layers of lunar mystery, each new discovery adds depth to our understanding, while simultaneously revealing how much we still have to learn. The far side remains a frontier in the truest sense, a place where the next observation or sample analysis might revolutionize our understanding of fundamental processes that operate throughout the universe. The hidden hemisphere that has watched over Earth for billions of years, unseen and unknown, is finally beginning to reveal its secrets. And as we continue to explore this alien yet familiar world, we find that the moon's far side is not just a destination for scientific discovery, but a mirror that reflects back our own curiosity, ingenuity, and endless desire to understand our place in the cosmos. The partnership between NASA and international space agencies in studying the far side has yielded discoveries that read like chapters from a cosmic detective novel. Each mission has added crucial pieces to a puzzle that spans billions of years, revealing a story of violence, transformation, and preservation that challenges our understanding of how worlds evolve. NASA's Lunar Reconnaissance Orbiter has served as our steadfast sentinel, monitoring the far side with instruments so sensitive they can detect temperature variations smaller than a degree and map surface features down to the size of a small boulder. For over a decade, this tireless observer has catalogued every crater, every ridge, every mysterious bright ray that streaks across the ancient terrain. Its cameras have captured images of Chinese landers touching down on alien soil, documenting humanity's expanding presence on this hidden world with the precision of a cosmic historian. But it's the data flowing from these observations that truly illuminates the farside's secrets. The Lunar Orbiter Laser altimeter aboard the spacecraft has measured the moon's topography with such precision that scientists can now create three-dimensional models accurate to within centimeters. These measurements reveal a landscape sculpted by forces so violent they defy imagination, where impact craters overlap like frozen ripples in a pond, each one telling the story of a cosmic collision that shook the moon to its core. The thermal mapping conducted by the Diviner instrument has revealed temperature patterns that speak to the moon's complex relationship with solar energy and its own internal structure. Some regions of the far side maintain temperatures hundreds of degrees different from their surroundings, hinting at compositional differences that may reflect the moon's tumultuous formation history. These thermal anomalies create a heat map of lunar evolution, showing where ancient impacts brought deep materials to the surface and where volcanic processes left their lasting signatures. Perhaps most intriguingly, the neutron detectors aboard various lunar missions have identified hydrogen signatures scattered across the far side landscape. These hydrogen concentrations often appear in the most unlikely places, far from the permanently shadowed polar regions where water ice was expected to concentrate. The distribution of these signals suggests that the moon's interaction with solar wind and cosmic bombardment has been creating and preserving water molecules in ways that weren't anticipated by early lunar models. The discovery that water might exist in forms and locations beyond our initial expectations has profound implications for understanding not just the moon, but the broader processes that distribute volatiles throughout the solar system. If water can be preserved in the lunar highlands through mechanisms we're only beginning to understand, similar processes might operate on other airless bodies throughout our cosmic neighborhood. Asteroids, the moons of outer planets, and even the surfaces of distant exoplanets might harbor water reservoirs that could support future exploration or even life itself. Recent laboratory analysis of lunar samples has revealed another layer of mystery in the Farside story. When scientists subject these ancient rocks to increasingly sophisticated analytical techniques, they uncover isotopic signatures that don't match any materials found elsewhere in the solar system. Some elements show ratios that suggest these rocks formed under conditions of extreme heat and pressure, possibly during the moon's earliest molten phase, when the entire body existed as a magma ocean. Other isotopic anomalies hint at more exotic processes. Certain rare elements appear in concentrations that could only be explained by cosmic ray bombardment over billions of years, or possibly by the incorporation of materials from the impacting bodies that created the moon's largest craters. Each rock sample becomes a time capsule, preserving information about events that occurred when our solar system was young and chaotic. when massive objects routinely collided and reshaped entire worlds. The seismic studies of the Moon continue to yield surprises that challenge our understanding of planetary interiors. When the Apollo-era seismometers detected moonquakes and impact events, they recorded vibrations that behaved unlike anything seen on Earth. The seismic waves would ring through the lunar interior for remarkably long periods, creating patterns that led some researchers to describe the Moon as ringing like a bell when struck. This unusual seismic behavior initially sparked speculation about the Moon's internal structure. Could the prolonged ringing indicate that the Moon was partially hollow, as some dramatic headlines suggested? More detailed analysis revealed a more nuanced explanation. The Moon's interior appears to be highly fractured and possibly contains zones of different density and composition that affect how seismic waves propagate. Rather than indicating a hollow interior, these patterns suggest a complex internal architecture shaped by billions of years of impact bombardment and thermal evolution. The far side's role in preserving this seismic information is crucial because it experiences different patterns of impact bombardment than the near side. The hemisphere facing away from Earth receives impacts from objects arriving from deep space, while the near side is partially shielded by Earth's gravitational influence. This difference in impact flux creates distinct seismic signatures that help scientists understand how bombardment patterns have varied over lunar history. Modern computer simulations now allow researchers to model these ancient moonquakes with remarkable detail, incorporating everything from the Moon's internal structure to the dynamics of impact events. When these models are compared with the actual seismic records preserved in Apollo-era data, they reveal insights about the Moon's formation and evolution that couldn't be obtained any other way. The far side serves as a natural seismometer, recording and preserving information about cosmic impacts that occurred billions of years ago. The magnetic field studies of the lunar far side have uncovered perhaps the most puzzling aspects of lunar evolution. Rocks from the far side preserve some of the strongest magnetic signatures found anywhere on the Moon, suggesting that this hemisphere experienced intense magnetic fields during certain periods of lunar history. These paleomagnetic records indicate that the Moon once possessed a global magnetic field that may have been comparable in strength to Earth's current field. The existence of this ancient lunar magnetosphere raises fundamental questions about the Moon's early thermal state and interior dynamics. Generating a planetary magnetic field typically requires convection in molten metallic cores, driven by the cooling and crystallization of iron-rich materials. The Moon's small size should have led to rapid cooling and solidification of its core. Yet the magnetic evidence suggests that core convection persisted for hundreds of millions of years longer than simple thermal models would predict. The far side's magnetic anomalies also show spatial patterns that correlate with major impact structures. Some of the strongest magnetic signatures are found at locations directly opposite to large impact basins, suggesting that basin-forming impacts may have enhanced magnetic field generation through shock-related processes. When a massive asteroid strikes one side of a planetary body, the shock waves converge at the antipodal point, potentially creating conditions that enhance magnetic field strength or preserve existing magnetization more effectively. Understanding these magnetic processes has implications that extend far beyond lunar science. Many small planetary bodies throughout the solar system show evidence of ancient magnetic fields that couldn't be explained by conventional core dynamo processes. The Moon's magnetic history may provide a template for understanding how magnetic fields are generated and preserved on worlds that lack the size and thermal energy to sustain long-lived core convection. The search for resources on the lunar far side has revealed deposits that could revolutionize space exploration. Beyond the water ice found in permanently shadowed craters, orbital surveys have identified concentrations of rare Earth elements, titanium, and other valuable materials scattered across the far-side landscape. These resource maps, created by combining data from multiple missions, show that the Moon's hidden hemisphere contains materials that could support extensive industrial operations in space. The distribution of these resources reflects the Moon's complex geological history. Rare Earth elements appear to be concentrated in regions where ancient impacts brought deep crustal materials to the surface. Titanium-rich minerals are found in areas where unique volcanic processes operated billions of years ago. Iron and other metals show concentrations that correlate with the locations of large impact events, possibly representing fragments of the metallic impactors themselves. But perhaps the most intriguing resource discovery involves the detection of helium-3, a rare isotope that could serve as fuel for advanced fusion reactors. This material, deposited on the lunar surface by billions of years of solar wind bombardment, exists in concentrations that could make lunar mining economically viable. The far side's lack of atmospheric protection means it has accumulated helium-3 over its entire geological history, creating reserves that could power human civilization for thousands of years. The technical challenges of extracting and processing lunar resources are substantial, but not insurmountable. Robotic mining systems capable of operating in the harsh lunar environment are under development, while processing techniques for separating valuable materials from lunar regolith are being tested in terrestrial laboratories. The reduced gravity and lack of atmospheric interference on the Moon could actually make some industrial processes easier than their terrestrial counterparts, particularly those involving high-temperature operations or the handling of toxic materials. The economic implications of lunar resource extraction extend beyond simple material wealth. Access to space-based resources could fundamentally alter the economics of space exploration, making it possible to construct spacecraft, habitats, and other infrastructure using materials that don't have to be launched from Earth's deep gravity well. A space-based industrial economy could enable missions to Mars and the outer planets that would be prohibitively expensive using Earth-based resources alone. The environmental considerations of lunar mining present unique challenges and opportunities. Unlike terrestrial mining, lunar resource extraction wouldn't directly impact ecosystems or atmospheric composition. However, the preservation of scientifically valuable lunar sites and the prevention of contamination from mining operations require careful planning and international coordination. The Moon's role as a natural laboratory for studying planetary processes could be compromised if mining operations aren't conducted with appropriate safeguards. The far side's potential as a location for astronomical observatories continues to drive mission planning at space agencies worldwide. The natural radio silence created by the Moon's blocking effect represents one of the most valuable scientific resources in the inner solar system. This electromagnetic quiet zone becomes increasingly precious as Earth's radio interference grows with advancing technology and expanding satellite networks. The proposed astronomical facilities for the far side range from individual specialized instruments to comprehensive observatory complexes that could revolutionize multiple fields of astronomy. Radio telescopes operating at frequencies blocked by Earth's ionosphere could detect signals from the cosmic dark ages, the period between the universe's initial cooling and the formation of the first stars. Optical telescopes, free from atmospheric disturbances, could conduct precision measurements of stellar positions and planetary motions with accuracy impossible from Earth-based facilities. The technical requirements for these astronomical installations push the boundaries of current robotics and space construction technologies. Deploying kilometer-scale antenna arrays or mirror assemblies on the lunar surface would require autonomous systems capable of precise construction operations without direct human supervision. The harsh lunar environment with its extreme temperature swings and abrasive dust, creates additional challenges for maintaining sensitive scientific equipment over extended periods. Power generation for far-side observatories presents particular challenges due to the extended lunar night. Solar panels alone cannot provide continuous power during the 14-day lunar night, requiring energy storage systems or alternative power sources such as nuclear reactors. The development of reliable long-duration power systems for lunar operations has applications beyond astronomy, potentially enabling sustained human presence and industrial operations throughout the solar system. The scientific returns from far-side astronomical observations could justify the substantial investments required. The ability to observe previously inaccessible radio frequencies would open entirely new windows on the universe, potentially revealing phenomena that remain completely unknown to current astronomy. The detection of signals from the cosmic dark ages could provide direct information about the universe's earliest epochs, complementing and extending the capabilities of space-based telescopes that observe in optical and infrared wavelengths. The coordination required for international lunar astronomical facilities presents both challenges and opportunities for space cooperation. No single nation possesses all the resources necessary to construct and operate major lunar observatories, making international collaboration essential for success. The development of shared lunar infrastructure could serve as a model for future cooperative ventures throughout the solar system, fostering peaceful cooperation in space exploration, while advancing scientific knowledge for all humanity. The cultural and philosophical implications of far-side exploration extend beyond scientific discovery into questions about humanity's relationship with the cosmos. For millennia, the moon has served as a symbol of mystery, change, and the unknown. The hidden hemisphere represented the ultimate frontier, a realm that existed beyond human perception and imagination. Now that we're beginning to explore and understand this hidden world, we're confronting fundamental questions about the far side's transformation from myth nature of discovery and the limits of human knowledge. Theacal realm to scientific laboratory reflects humanity's evolving relationship with the unknown. Where ancient cultures saw divine mystery, modern science finds natural processes operating according to physical laws. Yet this scientific understanding doesn't diminish the wonder of discovery. It amplifies it by revealing the true scale and complexity of the processes that shaped our cosmic neighborhood. The democratization of lunar exploration through international cooperation and commercial space ventures is creating opportunities for broader participation in far-side discovery. Amateur astronomers contribute to observations that complement professional missions, while citizen science projects allow individuals worldwide to participate in analyzing lunar data and identifying new phenomena. This broader engagement helps ensure that the benefits of lunar exploration extend beyond academic institutions to inspire and educate people throughout the world. The educational value of far-side exploration cannot be overstated. Students following current missions learn firsthand how scientific knowledge develops through careful observation, hypothesis testing, and international collaboration. The real-time nature of modern space missions allows people worldwide to experience the excitement of discovery as it unfolds, creating emotional connections to scientific exploration that can last a lifetime. The challenges of exploring the far side also serve as catalysts for technological innovation, with applications far beyond space exploration. The autonomous systems developed for lunar operations advance robotics technology with applications in manufacturing, healthcare, and environmental monitoring. The communication systems required for far-side missions improve satellite technology and deep space navigation. The life support and resource utilization technologies needed for sustained lunar operations contribute to sustainability efforts on Earth. As we look toward the future of far-side exploration, the trajectory of discovery seems poised to accelerate dramatically. Multiple space agencies and commercial organizations are developing missions that will expand our presence on the hidden hemisphere. Advanced robotic systems will conduct increasingly sophisticated scientific investigations, while human explorers may eventually establish permanent research stations that enable continuous observation and experimentation. The integration of artificial intelligence and machine learning into far-side exploration will amplify human capabilities and enable discoveries that might be missed by traditional analytical approaches. Automated systems will monitor the lunar environment continuously, identifying transient phenomena and unusual patterns that require further investigation. Machine learning algorithms will analyze vast datasets collected by orbital missions, potentially revealing subtle correlations and trends that escaped human notice. The far side's role as a stepping stone to deeper space exploration is becoming increasingly apparent as mission planners develop strategies for Mars exploration and outer planet missions. The Moon's lower gravity and lack of atmospheric resistance make it an ideal location for launching and refueling deep space missions. Far-side facilities could serve as staging areas for interplanetary expeditions, providing the infrastructure and resources needed for sustained exploration throughout the solar system. The lessons learned from far-side exploration will inform our understanding of other mysterious worlds throughout the universe. The techniques developed for studying the Moon's hidden hemisphere will be applicable to investigations of asteroids, comets, and the moons of outer planets. The scientific frameworks created to interpret far-side geology will help us understand planetary processes operating on worlds orbiting distant stars. But perhaps the most profound impact of far-side exploration lies in its potential to reshape our perspective on Earth itself. Seeing our planet from the far side of the Moon, suspended in the blackness of space as a brilliant blue marble, provides a perspective on our world's uniqueness and fragility that no amount of description can convey. This cosmic perspective, available to only a handful of Apollo astronauts in the past, may become increasingly accessible as far-side exploration expands. The hidden hemisphere that remained mysterious for all of human history continues to yield secrets that challenge our understanding while inspiring our imagination. Each new discovery adds depth to our knowledge, while simultaneously revealing how much remains to be learned. The far side stands as both destination and symbol, representing humanity's endless quest to understand our place in the universe, while demonstrating our capacity to transform the unknown into the familiar through careful observation and analysis. As robotic explorers continue their patient work in the lunar landscape and human explorers prepare for their return to the Moon, the far side awaits with secrets that have been preserved for billions of years. Whether these secrets involve ancient impact processes, exotic mineral formations, or resources that could transform space exploration, they represent opportunities for discovery that could reshape our understanding of planetary science and our future in space. The far side of the Moon, once the realm of speculation and imagination, has become humanity's newest frontier for scientific discovery and technological achievement. As we continue to explore this alien yet familiar world, we find that each answer leads to new questions. Each discovery opens new avenues of investigation, and each mission brings us closer to understanding the complex processes that shaped our solar system and continue to influence our cosmic future. In the gentle light of distant stars, the far side continues its ancient vigil, preserving the stories of cosmic violence and planetary birth that occurred when our solar system was young. Now, for the first time in its 4.5 billion year history, this hidden world has human witnesses to its secrets. And as we learn to read the stories written in its ancient rocks and preserved in its impact-scarred landscape, we discover that the far side of the Moon is not just a destination for exploration, but a bridge connecting us to the deepest mysteries of cosmic evolution and our own origins in the stars. The technological marvels enabling our exploration of this hidden realm continue to push the boundaries of what we thought possible in the harsh environment of space. As we delve deeper into the far side's mysteries, we encounter engineering challenges that would have seemed insurmountable just decades ago. Yet today's robotic explorers navigate these obstacles with remarkable sophistication. Consider the delicate ballet performed by NASA's Deep Space Network as it maintains communication with missions venturing beyond the moon's protective embrace. When spacecraft disappear behind the lunar horizon, ground controllers must rely on precisely choreographed orbital mechanics to re-establish contact hours later. This cosmic game of hide and seek requires split-second timing and mathematical precision that showcases humanity's growing mastery of celestial navigation. The instruments aboard these far-flung explorers represent marvels of miniaturization and ruggedness. Spectrometers no larger than a shoebox can identify the chemical composition of rocks from orbit, while cameras with resolution so fine they could spot a dinner table from hundreds of kilometers above the surface capture images that reveal the moon's hidden topography in breathtaking detail. These technological achievements, born from the necessity of studying an inaccessible world, often find their way back to Earth in applications that benefit all of humanity. The data streams flowing back from the far side paint an increasingly detailed portrait of a world that defies simple categorization. Recent orbital surveys have revealed mineral distributions that follow patterns unlike anything found on the familiar near side. Concentrations of rare elements appear in unexpected locations, often associated with ancient impact structures that excavated materials from deep within the lunar interior. These mineral maps tell stories of cosmic violence and geological processes that operated under conditions far removed from our earthly experience. When massive asteroids struck the young moon billions of years ago, they didn't simply create craters. They fundamentally altered the chemical landscape, mixing materials from different depths and creating deposits that preserve information about the moon's interior composition in ways that would be impossible to achieve through any other means. The rare earth elements scattered across the far-side landscape represent more than scientific curiosities. These materials, essential for modern electronics and advanced technologies, exist in concentrations that could potentially support future space-based industries. The prospect of extracting these resources from the lunar surface, while technically challenging, offers tantalizing possibilities for reducing humanity's dependence on terrestrial mining operations. But perhaps more intriguing than the known resources are the materials we haven't yet identified. Each new spectroscopic survey reveals previously undetected mineral phases and chemical compounds that expand our understanding of what's possible in planetary formation processes. Some of these exotic materials may have formed under pressure and temperature conditions that existed nowhere else in the solar system, creating natural laboratories for studying extreme physics. The thermal environment of the far side presents its own fascinating complexities. Without the moderating influence of Earth's reflected sunlight, temperatures on the hidden hemisphere can plunge to depths that approach absolute zero in permanently shadowed regions. These cosmic freezers preserve volatile materials that would quickly sublimate elsewhere, creating natural repositories for studying the early solar system's chemical inventory. The discovery of temperature anomalies scattered across the far-side landscape hints at subsurface processes that remain poorly understood. Some regions maintain temperatures significantly different from their surroundings, possibly indicating underground heat sources or unusual thermal conductivity in the lunar regolith. These thermal signatures create a kind of underground weather map that reveals how heat flows through the moon's interior in ways that surface observations alone could never detect. The seismic mysteries of the moon continue to perplex researchers decades after the Apollo missions first deployed sensitive earthquake detectors on the lunar surface. The peculiar way that moonquakes propagate through the lunar interior suggests structural complexities that challenge our understanding of how planetary bodies form and evolve. Rather than the simple layered structure that early models predicted, the Moon appears to possess internal architecture that includes zones of different density, composition, and possibly even voids created by ancient impact events. These seismic anomalies become even more intriguing when viewed in the context of the far side's unique bombardment history. The hidden hemisphere has experienced a different pattern of impacts than the near side, receiving projectiles from deep space that arrived with different velocities and compositions than those that struck the Earth-facing side. This asymmetric bombardment may have created internal structures that vary between the two hemispheres, contributing to the seismic signatures that make the Moon ring like a bell when struck by meteorites. Recent computer simulations of these ancient impact events reveal processes so violent they strain the imagination. When asteroids travelling at dozens of kilometers per second struck the early Moon, they didn't simply excavate craters. They sent shockwaves racing through the entire lunar body, creating pressure pulses that temporarily liquefied solid rock and generated temperatures exceeding those found in stellar cores. The reverberations from these cosmic collisions may have created the internal structures that continue to influence how seismic waves propagate through the Moon today. The magnetic field studies of lunar rocks have revealed another layer of mystery in the far side story. The ancient magnetism preserved in highland samples suggests that the Moon once possessed a global magnetic field that may have rivaled Earth's in strength. This discovery overturned previous assumptions about the thermal evolution of small planetary bodies and raised fundamental questions about how magnetic fields are generated and sustained. The far side appears to preserve some of the strongest magnetic signatures found anywhere on the Moon, possibly because the thicker crust provided better protection for these ancient magnetic records. Some researchers propose that the magnetic field itself may have contributed to the hemispheric differences we observe today, influencing how solar wind particles interacted with the lunar surface and potentially affecting the retention of volatile materials in different regions. The correlation between magnetic anomalies and major impact structures suggests that basin-forming collisions may have played a role in magnetic field generation or preservation. When massive impactors struck the Moon, they may have created temporary magnetic fields through shock-induced processes, or they may have enhanced existing fields through complex electromagnetic interactions. Understanding these processes could provide insights into magnetic field generation on other worlds throughout the solar system. The water story of the far side continues to evolve as more sophisticated detection methods reveal the complex ways that hydrogen and oxygen can be stored in the lunar environment. Beyond the obvious ice deposits in permanently shadowed craters, researchers have identified water signatures in mineral structures, bound within crystal lattices, and possibly even as thin films on grain surfaces throughout the highland regions. This widespread distribution of water in various forms suggests that the Moon's interaction with solar wind particles and cosmic bombardment has been creating and preserving water molecules through multiple pathways over billions of years. The solar wind continuously deposits hydrogen atoms on the lunar surface, where they can interact with oxygen-bearing minerals to form hydroxyl groups and eventually water molecules. While most of this water quickly escapes to space, some becomes trapped in mineral structures or migrates to cold regions where it can accumulate over geological timescales. The implications of this distributed water resource extend far beyond simple resource utilization. The presence of water in unexpected forms and locations suggests that similar processes may operate on other airless bodies throughout the solar system. Asteroids, the moons of outer planets, and even the surfaces of distant exoplanets might harbour water reservoirs created through analogous mechanisms, potentially expanding the number of worlds that could support future exploration or even life itself. The chemical diversity revealed by analysis of far-side materials continues to challenge our understanding of planetary formation processes. Samples returned by recent missions show isotopic signatures that don't match any materials found elsewhere in the solar system, suggesting that the Moon may have experienced unique evolutionary processes that operated under conditions unlike those found on other worlds. Some of these chemical anomalies appear to be related to the Moon's formation through a giant impact event, while others may reflect subsequent processing by cosmic bombardment, solar wind implantation, or internal differentiation processes. Each unusual isotopic ratio or unexpected elemental concentration provides clues about the conditions that existed during different periods of lunar history, helping researchers reconstruct the complex sequence of events that shaped our nearest celestial neighbour. The preservation of these chemical signatures on the far side may be related to the hemisphere's different geological history. The limited volcanic activity on the hidden side meant that fewer ancient materials were buried or altered by later geological processes, creating a kind of chemical museum that preserves information about the Moon's earliest epochs. This preservation makes the far side particularly valuable for understanding not just lunar evolution, but the broader processes that shaped all terrestrial planets during the solar system's violent youth. The atmospheric studies of the lunar far side have revealed another unexpected aspect of this supposedly airless world. While the Moon lacks a substantial atmosphere in any conventional sense, it does possess an extremely tenuous envelope of gases that varies in composition and density depending on location and time. The far side contributes unique components to this minimal atmosphere through processes that differ from those operating on the near side. Solar wind particles striking the far side surface liberate atoms and molecules through sputtering processes, while thermal cycling between lunar day and night drives sublimation and deposition of volatile materials. Micrometeorite impacts continuously vaporize small amounts of surface material, adding their own contributions to the Moon's gossamer atmosphere. These processes create a dynamic, ever-changing atmospheric environment that, while incredibly thin by terrestrial standards, plays important roles in transporting materials across the lunar surface. Here, understanding the Moon's minimal atmosphere has implications for future exploration and resource utilization. Even trace amounts of atmospheric gases can affect sensitive scientific instruments, while dust particles suspended in the thin atmosphere could pose hazards to equipment and human explorers. The electrostatic properties of lunar dust, enhanced by solar wind charging effects, create additional challenges for operations in the lunar environment. The ongoing geological activity on the Moon, while minimal compared to Earth, continues to shape the far-side landscape in subtle but measurable ways. Thermal expansion and contraction create stress fractures in surface rocks, while the gradual sublimation of subsurface ice deposits can cause small-scale surface changes. These processes operate so slowly that their effects are barely perceptible over human timescales, but they accumulate over millions of years to create measurable modifications to the lunar landscape. Recent observations have identified fresh crater rays and impact features that provide evidence for ongoing bombardment of the far side by micrometeorites and larger objects. While major impacts are rare in the current epoch, the continuous rain of smaller projectiles gradually modifies surface features and mixes the uppermost layers of lunar regolith. This space weathering process creates the characteristic appearance of lunar highland materials, while also affecting the preservation and accessibility of resources like water ice and rare minerals. The tidal effects that lock the Moon in synchronous rotation with Earth continue to influence the far side through subtle gravitational forces that create stress patterns in the lunar crust. These tidal stresses, while much weaker than those that originally shaped the moon's rotation, may contribute to the occasional moonquakes detected by seismic monitoring systems. The far side experiences these tidal forces differently than the near side due to its greater distance from Earth, potentially contributing to the structural differences observed between the two hemispheres. The role of the far side in the broader Earth-Moon system continues to evolve as tidal friction gradually increases the distance between our planet and its natural satellite. This slow orbital evolution affects the gravitational relationship between Earth and Moon, potentially influencing everything from tidal patterns in Earth's oceans to the stability of the Moon's rotation. Understanding these long-term changes helps researchers predict how the Earth-Moon system will continue to evolve over astronomical timescales. The cultural impact of far-side exploration extends beyond scientific discovery into realms of art, literature, and human imagination. The transformation of the Moon's hidden hemisphere from a realm of mystery and speculation into a destination for scientific investigation reflects humanity's evolving relationship with the unknown. Where previous generations could only imagine what lay beyond the lunar horizon, we now possess detailed maps and chemical analyses of this alien landscape. This transformation from mystery to knowledge doesn't diminish the wonder of discovery. Instead, it reveals the true complexity and beauty of natural processes operating on scales that dwarf human experience. The far side's ancient impact basins and pristine highland terrain speak to cosmic events so violent and transformative that they challenge our ability to comprehend the forces that shaped our solar system's early history. The educational opportunities created by far-side exploration inspire new generations of scientists, engineers, and explorers who will carry forward humanity's quest to understand our cosmic environment. Students following current missions learn not just facts about lunar geology and planetary science, but also about the processes of discovery, hypothesis testing, and international cooperation that drive modern scientific investigation. The technological innovations required for far-side exploration continue to find applications in fields far removed from space science. The autonomous systems developed for lunar operations advance robotics technology with applications in manufacturing, healthcare, and environmental monitoring. The communication systems required for far-side missions improve satellite technology and deep space navigation capabilities. The materials science breakthroughs needed for surviving the harsh lunar environment contribute to advances in everything from electronics to construction materials. As we stand on the threshold of an era that will see sustained human presence on the far side, we're preparing to answer questions that have intrigued humanity for generations while simultaneously discovering new mysteries that we couldn't have imagined before beginning this journey of exploration. The hidden hemisphere that remained beyond human reach for all of recorded history is becoming humanity's newest frontier, offering opportunities for discovery that could reshape our understanding of planetary science and our future among the stars. The far side of the moon represents more than a destination for scientific investigation. It embodies humanity's capacity to transform the impossible into the achievable through patience, ingenuity, and collaborative effort. Each successful mission to the hidden hemisphere demonstrates our growing ability to extend our reach beyond the boundaries of our home planet. While each new discovery reminds us that the universe holds secrets we're only beginning to uncover. Tonight, as you rest beneath the familiar glow of the moon's near side, remember that just beyond that bright horizon lies a world of wonders that our species is only now learning to explore. The same gravitational forces that create the tides in Earth's oceans and stabilize our planet's rotation have preserved for us a natural laboratory where the stories of cosmic evolution remain written in stone, waiting for human curiosity and technological capability to finally read their ancient messages. The journey to understand the far side continues, with each passing day bringing new data from robotic explorers and new plans for future missions that will expand our presence on this alien yet familiar world. In the grand sweep of cosmic time, our exploration of the moon's hidden hemisphere has barely begun. Yet already, we've learned enough to transform our understanding of how worlds form, evolve, and preserve the stories of their cosmic heritage. The far side awaits, patient and mysterious, holding secrets that span the entire history of our solar system. As we prepare for the next chapter of lunar exploration, we carry with us the accumulated wisdom of generations of astronomers, engineers, and dreamers who dared to imagine that humanity could one day venture beyond the familiar boundaries of our earthly home to explore the wonders that lie hidden among the stars. As we drift deeper into our exploration of this hidden world, we encounter discoveries that push against the very boundaries of what we thought possible in planetary science. The seismic mysteries recorded during the Apollo era continue to perplex researchers with their haunting implications. When sensitive instruments detected moonquakes reverberating through the lunar interior, they captured something that defied every earthly comparison we possessed. The moon, when struck by meteorite impacts or shaken by internal tremors, would ring like a cosmic bell for hours, sometimes maintaining its vibrational song for periods that seemed to stretch beyond reason. This prolonged ringing created whispers of speculation that have echoed through decades of scientific discourse. Could our celestial companion harbour vast hollow chambers within its ancient heart? The data painted pictures of seismic waves travelling through an interior so fractured and complex that some researchers wondered whether conventional models of planetary formation could account for such unusual behaviour. Dr. Maurice Ewing, one of the principal investigators analysing these seismic signatures, famously remarked that the moon's interior seemed to behave as though it contained large void spaces or zones of drastically different density. The implications sent ripples through the scientific community, challenging fundamental assumptions about how worlds like ours are constructed. Yet as more sophisticated analysis techniques emerged, a more nuanced understanding began to take shape. The far side's thicker crust appears to play a crucial role in these seismic anomalies. When shock waves from impacts or moonquakes encounter the dense highland materials that dominate the hidden hemisphere, they propagate in ways that create the prolonged ringing effects that so puzzled early researchers. Rather than indicating hollow chambers, these signatures likely reflect a complex internal architecture shaped by billions of years of cosmic bombardment and thermal evolution. But the mystery deepens when we consider the asymmetric nature of these seismic patterns. Vibrations travelling through different regions of the moon exhibit distinct characteristics that suggest the interior is far from uniform. Some pathways seem to conduct seismic energy more efficiently than others, creating a kind of acoustic map that reveals structural variations invisible to surface observations. The implications extend beyond mere scientific curiosity. Understanding the moon's internal architecture becomes crucial as we plan for future exploration and resource extraction. Will drilling operations encounter void spaces or unusually dense materials? How will the propagation of human-generated vibrations affect sensitive scientific instruments? These questions transform abstract seismic data into practical engineering considerations that will influence the design of future lunar facilities. Recent computer simulations have begun to model these seismic behaviours with increasing sophistication, incorporating everything from the moon's formation history to the effects of individual impact events. The results suggest that the far side's unique bombardment history may have created internal fracture networks that extend deep into the lunar interior. These fractures, invisible from the surface but detectable through their influence on seismic wave propagation, represent scars from cosmic collisions so violent they permanently altered the moon's internal structure. The preservation of these ancient fracture systems on the far side contrasts with the near side, where extensive volcanic activity may have filled or altered many internal voids. This difference in geological processing means that the hidden hemisphere serves as a more complete archive of the Moon's violent past, preserving structural evidence of events that occurred during the solar system's most chaotic epochs. The search for volatiles on the far side has revealed distribution patterns that challenge our understanding of how water and other light elements behave in the lunar environment. While the most obvious concentrations exist in permanently shadowed craters near the poles, orbital surveys have detected hydrogen signatures scattered throughout highland regions, where conventional models suggest such materials should have been lost to space long ago. These unexpected volatile deposits appear to follow patterns that correlate with ancient impact structures, suggesting that cosmic collisions may have created local environments capable of preserving water and other light elements over geological timescales. Some craters seem to act as natural cold traps, even when not permanently shadowed, maintaining temperatures low enough to prevent rapid sublimation of ice deposits. The discovery of these distributed water resources transforms our understanding of lunar resource potential. Rather than being restricted to polar regions for water access, future missions might tap into widely scattered deposits that could support exploration activities throughout the far side. This geographical flexibility would allow mission planners to choose landing sites based on scientific value or strategic importance, rather than being constrained by resource availability. But the most intriguing aspect of far-side water distribution lies in its potential origins. Isotopic analysis of lunar ice samples reveals signatures that don't match terrestrial water, suggesting that at least some of the Moon's volatile inventory may have been delivered by comets and asteroids during the late heavy bombardment. These ancient ice deposits preserve chemical fingerprints of the early solar system, potentially containing information about the composition of the primordial disk from which all planets formed. The implications ripple outward to encompass questions about water delivery throughout the solar system. If the Moon can preserve water ice from ancient cometary impacts, similar processes might have operated on other worlds, potentially explaining the presence of water on Mars, the moons of outer planets, and even the surfaces of large asteroids. Understanding lunar water preservation mechanisms could provide templates for identifying water resources on worlds we have yet to explore. The technological challenges of extracting and utilizing these far-side water deposits are formidable but not insurmountable. Robotic systems capable of operating in the extreme thermal environment of permanently shadowed regions are under development, incorporating lessons learned from terrestrial operations in polar environments. The processing techniques required to extract water from lunar regolith and convert it into useful forms, like drinking water or rocket fuel, are being refined through laboratory experiments and field tests. The economic potential of lunar water extraction extends far beyond simple resource utilization. Water can be split into hydrogen and oxygen, creating rocket fuel that could enable refueling operations throughout the inner solar system. Rather than carrying all necessary propellant from Earth's deep gravity well, spacecraft could refuel at lunar facilities, dramatically reducing the cost and complexity of missions to Mars and beyond. This vision of the Moon as a cosmic refueling station transforms the hidden hemisphere from a scientific curiosity into a strategic asset for space exploration. Far-side facilities could serve as staging areas for deep space missions, providing not only fuel but also maintenance facilities, supply depots, and crew rest areas for long-duration interplanetary voyages. The unique electromagnetic environment of the far side continues to attract attention from astronomers eager to exploit its natural radio silence. Earth's growing electronic noise pollution makes ground-based radio astronomy increasingly challenging, while the proliferation of satellites and space debris creates additional interference that affects even space-based observations. The far side's position, permanently shielded from terrestrial radio sources, represents one of the quietest electromagnetic environments in the inner solar system. This natural radio sanctuary becomes increasingly valuable as we develop more sensitive astronomical instruments capable of detecting ever fainter signals from distant cosmic sources. Radio telescopes operating from the far side could potentially observe frequencies that are completely blocked by Earth's ionosphere, opening entirely new windows on the universe that remain inaccessible to ground-based facilities. The scientific potential of far-side radio astronomy extends across multiple fields of research. Low-frequency observations could detect signals from the cosmic dark ages, providing direct information about the universe's earliest epochs, when the first stars and galaxies were forming. Solar system astronomy could benefit from continuous monitoring of planetary magnetospheres and solar wind interactions without interference from Earth's radio environment. The proposed Lunar Crater Radio Telescope represents perhaps the most ambitious astronomical project ever conceived for the Moon's surface. This facility would deploy a kilometre-diameter antenna array within a suitable impact crater, creating a natural, bowl-shaped reflector that could focus radio waves with unprecedented precision. The technical challenges of constructing such a facility using robotic systems are substantial, requiring advances in autonomous construction techniques and precision manufacturing in the harsh lunar environment. But the scientific returns could justify the enormous investment required. A lunar radio telescope of this scale would possess collecting area exceeding all terrestrial radio facilities combined, while operating in an environment free from atmospheric interference and electronic noise. The observations possible with such an instrument could revolutionize our understanding of cosmic evolution, potentially detecting phenomena that remain completely unknown to current astronomy. The coordination required for international lunar astronomical facilities presents both challenges and opportunities for space cooperation. No single nation possesses all the resources necessary to construct and operate major far-side observatories, making collaborative efforts essential for success. The development of shared lunar infrastructure could serve as a model for future cooperative ventures throughout the solar system. The legal and regulatory frameworks for far-side astronomical operations remain largely undeveloped, creating potential complications for international collaboration. Questions about territorial rights, resource utilization, and environmental protection on the Moon require careful consideration to ensure that astronomical facilities can operate without conflicts over jurisdiction or access rights. The biological implications of far-side exploration touch on some of the most profound questions in astrobiology and the search for life beyond Earth. While the Moon itself is unlikely to harbour indigenous life, the materials preserved on its surface may contain information about biological processes that operated elsewhere in the solar system during its earliest epochs. Organic molecules delivered to the Moon by comets and asteroids could preserve chemical signatures of biological activity that occurred on other worlds billions of years ago. The far side's limited geological processing means that such materials might remain intact longer than similar compounds on more active planets, creating natural archives of ancient biological information. The search for these potential biosignatures requires sophisticated analytical techniques capable of distinguishing between organic molecules of biological origin and those created through non-biological processes. Laboratory studies of lunar samples continue to push the boundaries of what's possible in detecting trace organic compounds, while theoretical models explore the conditions under which biological molecules might survive the harsh environment of interplanetary space. The preservation of organic materials on the far side also has implications for contamination control during future exploration. Earth-based organisms carried to the moon on spacecraft could potentially survive in protected environments, creating false positive signals in searches for indigenous or ancient biological materials. Developing protocols to prevent such contamination while enabling meaningful biological research requires careful balance between scientific objectives and planetary protection requirements. The philosophical dimensions of far-side exploration extend beyond scientific discovery into questions about humanity's relationship with the cosmos and our responsibilities as explorers of other worlds. The transformation of the moon's hidden hemisphere from a realm of mystery and speculation into a destination for systematic investigation reflects our species' growing capability to extend our reach beyond the boundaries of our home planet. This expansion of human presence into the cosmos carries with it obligations to preserve the scientific value of the environments we explore while ensuring that our activities don't compromise future opportunities for discovery. The moon serves as humanity's first testing ground for developing ethical frameworks for space exploration that balance scientific curiosity with environmental stewardship. The cultural significance of the far side also evolves as our understanding of this hidden world grows more sophisticated. Ancient civilizations created myths and legends about the moon's mysterious nature, but none could have imagined the complex geological processes and resource potential that modern science has revealed. The hidden hemisphere represents both a culmination of human curiosity and a starting point for even grander adventures among the stars. The technological legacy of far-side exploration extends far beyond lunar science into fields that benefit all of humanity. The autonomous systems developed for operating in the challenging lunar environment advance robotics technology with applications in healthcare, manufacturing, and environmental monitoring. The communication systems required for far-side missions improve satellite technology and deep space navigation capabilities throughout the solar system. The materials science innovations needed for surviving the harsh lunar environment contribute to advances in construction, electronics, and energy storage that find applications in terrestrial industries. The life support and resource utilization technologies developed for sustained lunar operations inform sustainability efforts on Earth, potentially contributing to solutions for climate change and resource scarcity. As we prepare for the next phase of far-side exploration, featuring both advanced robotic missions and the eventual return of human explorers to the lunar surface, we carry with us the accumulated knowledge of generations of scientists, engineers, and visionaries who dared to imagine that humanity could venture beyond the familiar boundaries of Earth to explore the wonders hidden among the stars. The far side of the moon awaits with patience that spans geological ages, preserving within its ancient rocks and impact-scarred landscape the stories of cosmic evolution that occurred when our solar system was young and chaotic. Each crater tells of violence on scales that dwarf human experience, while each mineral grain carries information about processes that operated under conditions we can barely imagine. Tonight, as the familiar face of the moon rises in your sky, remember that just beyond that bright horizon lies a world of mysteries that our species has only begun to explore. The same gravitational dance that created the tides and stabilized Earth's rotation has preserved for us a natural museum where the deepest secrets of planetary formation remain written in stone, waiting for human curiosity to unlock their ancient wisdom. The journey continues with each new mission, adding chapters to this cosmic story, each discovery revealing both answers to long-held questions and entirely new mysteries that challenge our understanding. In the vast sweep of cosmic time, our exploration of the moon's hidden hemisphere represents just the opening pages of a much longer story about humanity's expanding presence among the worlds that share our corner of the galaxy. The far side calls to us across the vacuum of space, offering opportunities for discovery that could reshape our understanding of how worlds form and evolve, while providing the resources and knowledge needed to carry human civilization beyond the boundaries of a single planet. As we answer that call, we join a conversation with the cosmos that began when the first humans looked up at the night sky and wondered what secrets lay hidden in the darkness between the stars. In the gentle stillness of the cosmic night, as automated systems continue their patient monitoring across lunar observatories worldwide, we find ourselves at the threshold of discoveries that may fundamentally alter our understanding of how worlds preserve their deepest secrets. The Chang'e missions have opened doorways we never knew existed, while NASA's orbital sentinels continue their decades-long vigil, watching and recording every subtle change across this alien landscape. The samples returned from the South Pole Aitken Basin have revealed volcanic activity that persisted far longer than our models predicted, suggesting thermal processes operating in the Moon's interior that we're only beginning to comprehend. These 2.8 billion-year-old basalts speak of a Moon that remained geologically active when we thought it should have been cold and dormant, challenging our fundamental assumptions about how small worlds lose their internal heat. But perhaps even more intriguing are the isotopic signatures found within these ancient rocks. The extreme depletion of strontium and neodymium suggests that the far side mantle underwent processing so extensive it created compositions unlike anything found elsewhere in the solar system. These chemical fingerprints point toward events of such magnitude that they reshaped the Moon's internal architecture on a hemispheric scale. The discovery of creep materials on the far side has sent ripples through the planetary science community, overturning decades of assumptions about lunar evolution. These potassium, rare earth element, and phosphorus-rich rocks were thought to be primarily a near-side phenomenon, helping to explain why volcanic activity was so much more extensive on the hemisphere we can see from Earth. Finding similar materials on the hidden side suggests that the Moon's early differentiation was far more complex and globally distributed than we ever imagined. This revelation forces us to reconsider fundamental questions about lunar formation. If heat-producing radioactive elements were more evenly distributed than surface features suggest, what processes concentrated them so dramatically on the near side? The answer may lie in the massive South Pole Aitken impact itself, an event so violent it may have triggered hemisphere-scale convection that redistributed materials throughout the Moon's interior. Computer simulations of this ancient collision paint pictures of destruction on scales that challenge our ability to comprehend. An asteroid hundreds of kilometers in diameter, traveling at cosmic velocities, strikes with energy equivalent to billions of nuclear weapons. The impact excavates materials from depths that may have reached the lunar mantle, while shockwaves race around the Moon's circumference, converging at the antipodal point with enough force to fracture bedrock on a global scale. The buried mass anomaly detected beneath the basin by NASA's Grail mission continues to perplex researchers. This concentration of dense material, equivalent to 5 times the mass of Hawaii's Big Island, may represent the fossilized remains of the impacting asteroid, its metallic core somehow embedded in the lunar mantle, like a cosmic bullet frozen in time. If this interpretation proves correct, we have preserved within our Moon a pristine sample of the primordial materials from which all planets formed. As we reach the end of our journey into the Moon's hidden realm, one truth becomes beautifully clear. The far side has transformed from humanity's greatest celestial mystery into our most promising frontier for discovery. From ancient crater records that preserve the solar system's violent birth to water ice deposits that could fuel our journey to Mars, this alien landscape continues to rewrite the story of how worlds form and evolve. Tonight, when you gaze up at that familiar lunar face, remember that just beyond lies a world of wonders waiting to welcome humanity home among the stars.